Okay, good afternoon, everyone. They say in English, you should not bring coals to Newcastle. And that's what I feel like talking about topological defects in France, since really practically the birthplace of this subject. Nevertheless, topological defects are really very, very important objects. They are global objects. They arise inevitably in any physical system that undergoes a quench, that undergoes breaking of global symmetries. They occur everywhere from the microscopic. The electron, since it has charge, breaks symmetries. There's a topological defect, and it has electric field line that goes all the way out to infinity, Coulomb field, so it's global. All through nanoscopic to mesoscopic systems, all the way to cosmology, when the analog of a global U1 symmetry breaking defect, which I'll discuss, is a cosmic string, and that's breaking at extremely, extremely high energy scales in the early universe, and like a millimeter of cosmic string, and its core has like the mass of the Rocky Mountains. I have quite a lot of introductory material at the beginning, not for the experts, so I hope you'll ask questions, and I hope everyone will learn at least one thing they don't know. So the notion begins with a system, any kind of energy, Hamiltonian, Lagrangian, action, free energy, that has some kind of symmetry, and I'll talk mostly about global symmetries. So you have this usually big symmetry of your starting point. But when a system orders and goes into a ground state, that ground state often is not unique. And there are two basic aspects to this. Start with the manifold I called M here, which is the entire manifold associated with the symmetry of, let's call it the energy. And then it's broken, the ground state has a different symmetry, the big symmetry I call G, and the ground state has a smaller symmetry I call H. And the manifold of inequivalent ground states is the coset space G mod H, because within H, you are moving around in equivalent ground states. But outside that, elements of G that are not moving around in H are different ground states. So you have essentially always an infinite dimensional manifold of inequivalent states. And this manifold has a lot of interesting information about your physical system embedded in its structure, and in particular its topology. So how do we study that topology? One of the main tools is homotopy theory, and at first sight it seems like a very bizarre kind of notion. You're interested in this manifold here, this M, okay? And what do? Here you study maps from known spaces, spheres of various dimensions, onto the manifold. So that seems like a really roundabout way of getting information about the manifold. But you have two things working in your favor. You have the simple space you started with, spheres of various dimensions like the circle, and you have the properties of the map. And with those two things, you can get quite a lot of information about this manifold M. For example, the zeroth homotopy group, pi zero, not the pion, tells you whether the manifold is connected or not. So you move around in one set of ground states, and you just cannot get to another component, another set of ground states. Pretty simple notion in topology, connectedness. The first homotopy group, which is maps from the circle to the manifold M, tells you whether the space is simply connected. And that means if a space is simply connected, you can take any circle, any loop on the manifold, each point on this loop is a ground state. And then you ask, can you shrink it down continuously? Doesn't have to be smooth, which a lot of people say. It only has to be continuous, not even differentiable necessarily. You just continuously shrink down that loop, always on the ground state manifold. And can you get down all the way to a point and stay on the ground state manifold? If not, the manifold is simply connected and there's some obstruction. So the first homotopic group is said to be non-trivial, and we'll discuss the nature of those obstructions, and they depend on the dimensionality in which you live. They can be lines or points, mostly. We'll discuss which is which. The second homotopy group, you map a whole two-dimensional sphere, so the surface of a ball, onto the manifold. And you ask if that's non-trivial. So can you wrap a whole two-sphere on the manifold of ground states and then shrink that down continuously or not? If that's non-zero, you have vanishing second homotopy group. And you can go higher. You can have maps from high-dimensional manifolds, like, for example, the three-sphere. The three-sphere, it turns out, you can wrap around a two-sphere. It's a Hopf map. Pretty weird, but that's possible, and that gives you non-trivial topological structures. Let's look at the case of line defects. Okay? So this will be non-vanishing pi1 living in a three-dimensional space. So how does that work? You have a three-dimensional loop on this manifold, and you contract it down. If you can contract it all the way down, staying on the ground state manifold, there's no obstruction. If there is an obstruction, that means there must be some point as you construct any loop, as you construct it down, you must reach a point that's not on the ground state manifold. That is a zero of the field, or a singularity in the derivative, but that's a point where you have to be off the ground state manifold. So that gives you a point. Now you take that ground state manifold and you can deform it continuously, and you get another loop going up here. And inside that loop, as you contract down, there must be another point off the ground state manifold. And then you connect them all up in three dimensions and you have a line. Okay? Well, that's a line defect, and it means everywhere along that line, you're off the ground state manifold. Typically, you say the order parameter is 0. You're in the disordered phase. So that's how you get a string, or a line defect, superfluid helium filament, superconducting vortex, and liquid crystal disclinations that we will discuss. The obstruction for pi0, the thing that separates two connected components, is usually a wall of some kind, a domain wall. Pi1 here, as I said, gives a line defect. If you go to pi2, you have this whole two-sphere, and now you're shrinking it down. So an obstruction there means there must be a point inside where you're off the ground state manifold. So in three dimensions, it's a point defect. And that's a monopole, an aster, a vortex, all of those structures. Now, two dimensions, which turns out to be remarkably rich, even richer in many ways than three dimensions. The dimension of the defects is a little different. So a domain wall, since you're only in two dimensions, separating two things will be just a line. Okay? A pi1 defect means you're shrinking the loop in a two-dimensional space, so then the obstruction is just one of those points. You can't connect them up in a line. So pi1 defect in two dimensions is a point. And let me give some examples. So XY model spins on a plane. You have a vector field in that case. And let's just fix the magnetization which describes the ordered space. So you have a magnetization vector, points out there, magnitude, let's just call it 1. That's a ground state. You can rotate, you can look at this line. It's clearer in three dimensions. We'll do that in a minute. This magnetization, this ground state, is a different ground state, even though the energies are the same. And so you have a whole circle's worth of ground states. Now, clearly, in this case, the manifold is connected. I can go from any point on the circle to any other point continuously. But the obstruction to shrinking down that loop to a point in 2 dimensions gives you the defect, which is the vortex, a point where magnetization is 0. And since you're in the disordered phase, it's essentially a phase with energy higher than the ground state. So we're talking about excited states, but we're talking about topologically, essentially unavoidable configurations or particles in the system. So the quantity that classifies this pi1 in this case as an integer, and it's associated with a winding number. If you go around like this and you wind once, that cannot be continuously deformed to winding 0 times. And here, the manifold itself is a circle, the space of ordered states, and you're mapping circle to a circle. So you can just wrap a circle, integer number of times around another circle, plus or minus, and that's the characteristic charge strength of that topological defect. And so you can just compute the integral of the angle as you go around and get this winding number. So here you already see this is a global quantity because I can take any loop whatsoever to compute this winding number, small, large, right out at infinity. It has to see that winding number because of the topological character of the defect. So here is, first one here is a +1, winding number 1 defect for a vector field in 2D. And what about this one? What's the winding number of this? So you have monopole, aster, source, and fluid mechanics. All of these structures you would have seen everywhere. What about this one? What's the winding number? Ananya, you're not allowed to answer. Yeah, it's 1 again. Okay? Even though everything is flowing in, if you go around a circle and look how that field rotates, it winds once. So that's also winding number 1. It looks like sort of the anti-defect, but it isn't as far as the topology is concerned. And when you wind around, it doesn't matter which way you wind around. You look at, as you go around, say counterclockwise or anti-clockwise, if the field is rotating in the same sense as you go around, it'll be a plus integer strength defect. You can go around the other way, and the field will still wind in the same sense as you go around. Okay? So it doesn't matter how you choose the orientation of the loop that you're going around. So here's, that's another sink and source are both +1s. Okay, so what's n equals -1? Okay, so this means you go around this way and the vector field has to rotate in the opposite sense, like this. And that gives you this structure shown here, which is usually called, mathematics called a crosshair, or hyperbolic flow in fluid mechanics, or a saddle. You have 2 things going in and 2 things going out. Okay, so same with ice models, statistical mechanics, things like that. And the weird thing is these n equals +1 has this radial symmetry, monopole or a vortex going around like that. And the -1 has a completely different symmetry. Okay? It has this 4-fold symmetry. So that's really, really interesting, I think. Let's look at winding number 2. Winding number 2 is a dipole. You go around once, and then you go around once, and then you go around again. 2. By the way, on the 2 sphere, it's usually said the sum of the strengths of the defects has to be the Euler characteristic of the 2 sphere. That's 2. And it's usually said, okay, so you need 2 defects. That's not right. You can have 1 defect of charge 2, the dipole. You have a single dipole on the 2 sphere. So this could be polar vortex, but a dipole, that could be the only one on the Earth. If you look at pi2, now you're trying to wrap the 2 sphere on a circle. There's no winding in that case. So second homotopy group for this vector field ordered like magnetization thing is 0. For a superfluid, you have wave functions that have a magnitude and a phase. The magnitude fixes the order, like superfluid density, and each angle theta is a distinct ground state. So again, it's a circle. The gradient of that circle is superfluid velocity. So again, the manifold of ground states is a circle, pi1 is z, and those are superfluid vortex strengths. So inside this loop here is the normal phase. Everywhere outside is the superfluid. So here you have a lot of energy in the disordered high temperature phase of the superfluid. That's a superfluid filament. Cosmic string, the simplest one, is again a breaking of a U1 symmetry. So you just have global U1, you have a phase. Inside the phase, you have, you're disordered. You're in the high temperature phase of some model of your field theory for early universe. And so that is huge amount of energy sitting in this core. And the idea of cosmic strings in cosmology, the simplest idea, is that the mass density inside that core can cause gravitational fluctuations, perturbations that accumulate, and one string can give rise eventually to one galaxy. That's the idea, and you can test it. Here's the explanation of Y line defect that I already gave you. Here's the loop. Here's the obstruction of shrinking it down to 0 if pi1's non-zero. Deform the manifold like that. Another point there, connect them up, and you get a line. That line has to be closed, otherwise you could pull the loop off the ends, or it could terminate on a boundary, and then you can't pull it off. So closed loops or lines terminating on boundaries. Let's look at the ferromagnet in 3 dimensions. So now you have a magnetization vector, and the absolute value of it is the magnetization. Now it's pointing in 3-dimensional space. So anywhere I point in 3-dimensional space, and I fix the magnitude, gives me a 2-dimensional sphere, S2. Okay? That's connected. You can go from one point to any other point. It's simply connected. You cannot lasso a basketball. If you take a loop on the 2-sphere, you can just pull it around nicely on itself, shrink it down always continuously to 0. So now you go to pretty basic ordered phase of magnetic systems, and there's no line defect. Pi2, you can then obviously wrap a 2-sphere on a 2-sphere, same as you wrap a circle on a circle. So there's and you can wrap it an integer number of times. So that gives you a strength, an integer strength defect, which is a point inside that point where magnetization is 0, high temperature phase. You have a disordered phase inside, magnetic phase outside. That is a monopole. And this object could be an elementary particle, a structure, configuration, excited state in this magnetic system. I said you could also, if you look at pi3, you can also wrap a 3-dimensional sphere on a 2-dimensional sphere. That gives rise to a defect called texture. There are no singularities, but what it is if you take a point on the target 2-sphere, the manifold of inequivalent ground states, and you pull it back to the 3-dimensional sphere, you have a loop, since you're going up 1 dimension. Now you take another point on the 2-sphere and pull it back, and you have another loop. And those 2 loops can intersect. And so you have a linking number. And what's key is it doesn't matter which 2 points you pick, you pull them back, and you'll get, for a given map, same non-trivial linking. So this is called the Hopf vibration. It's like on the 2-sphere, you have a circle everywhere, but the circles are twisted as you go around, such that the manifold is not just S2 times S1. So this is a texture-like defect. Any questions? Okay. Let's go to liquid crystals, where we'll stick for most of the rest of the talk. And here's where bringing coals to Newcastle here. The liquid crystal is a dramatically different field. Liquid crystal is defined by an orientation where things line up in order, okay? And they line up with just along some line. So you have mathematically a line field, not a vector field. And that is a fundamentally different object and actually quite tricky to work with. And let's look at its topological defects. If you insist on calling it a vector field, you have to identify it with the inverted vector field. So we often talk about a director N, which is a vector field with two heads or headless. It's really kind of backwards, but it's all in the literature. It's really just a line. And lines are projective space, like rays in quantum mechanics or projective geometry. You're just looking in some orientation. So let's look at so the manifold now. It's just like magnetization. You can have an ordered phase from a disordered phase where the orientations are random, an ordered phase where you pick out a preferred orientation, fix the magnitude, you again get a two-sphere, right? But you have to identify one point on the two-sphere, say North Pole, with the South Pole, the inverted point. Those 2 points are the same. Okay? So that is S2 mod Z2, change of sign. Now, this is a real projective space, in this case, two-dimensional space, so RP2, basis of projective geometry. And here, get something new. It's connected, fine. But it's not simply connected. Unlike ferromagnetic case, it's not simply connected. And how can you understand that? You take a loop on this RP2. Here, say, if I take a loop that just goes around in any part of this hemisphere or all the way down, I can clearly contract it to a point, right? But now let's take a loop. Let's take a path from the North Pole to the South Pole, or any point to its inverted point. I go along, nice. I hit here, this is the same point. That's a closed loop. And I cannot continuously break that to one that shrinks down. That is the topological obstruction. I go around and I'm back where I started, but far away kind of thing. So I have to cut to reduce to the trivial case. So that's how RP2, governing ordered liquid crystalline phases in 3D, is not simply connected. That means it has pi1 defects. Great. More structure than a ferromagnet. Technically, how do you compute this? The first homotopy group of a coset-like space, G mod H, is actually the zeroth homotopy group of the subspace in the coset H, if the top one, G, is simply connected. That's a theorem. So in this case, we have S2 mod Z2. S2 is simply connected, pi1 is 0. So we just have to compute pi 0 of Z2. And Z2 has two disconnected components, 1 and -1. You cannot go from 1 to -1 continuously. We know that from quantum mechanics also. Now, so, okay, connected, but we have pi1 defects. Pi2 of RP2 is also Z. And the reason is, if you look at, it's basically because the manifold, if you look at it geometrically, is a whole hemisphere. You identify northern hemisphere with the southern hemisphere, and you identify the boundary circle, inverted points, but that still has a two-sphere on it. And so you can wrap a two-sphere on the two-sphere associated with the projected space. So that's also an integer, and those are monopoles, point defects for a liquid crystal. Pi3, I already told you, is also non-zero because of the S2. In these last two cases, the mod by inversion symmetry doesn't change the topology. So we have what I call the texture, non-singular light defect. So in this simple system, supposedly simple, we have 3 of the 4 first sets of relevant homotopy groups in one system, pi 1, pi 2, pi 3. Much better than a ferromagnet. And this is just a fantastic. It's very, very rich. And in fact, the name of liquid crystalline order, nematic, comes from the Greek nema. And nema means thread. So that is the line defect of a liquid crystal. So the very structure of the ordered phase came from observations of these disclination lines. And it was named, if I got the history right, by Georges Friedel. So again, Colston, Newcastle, studied by Grandjean, Boulogand. Lots and lots of wonderful early work on these structures. Here's a picture of line defects. These are the elementary strength ones, the thicker ones are strength 1 up from that. This is a picture actually made by Maurice Clément. 2 nice reviews of the subject from 45 years ago by David Merment and Louis Michel, who is at IHES. Here's a nice picture. Here's if you need to know, if you want to know the structure of the free energies, the energies and so on, you go to this great book here. Now, that's 3D. Now let's go down to 2D. Oh, okay, should be easier. But not quite, because now let's look at the topology of liquid crystalline order, 2 dimensions. So now you're just orienting here, 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 or here. So each ordered phase, each nematic ordered ground state is a point now on 1-dimensional circle. And so let's look at pi 1 of this R, and this is S2 mod Z2 is, or S1, it should be, sorry, that's a typo. S1 mod Z2 is RP1. And let's look at its first homotopy group. So now we have a circle, and we identify antipodal points. So we can take half of the circle, semicircle, and then it ends here, and we have to identify this point with that point. So we close it up, we get topologically another circle. So pi 1 for this 2-dimensional case is again, is integers now. Before we had Z2. So in 3 dimensions, the Z2 means it's trivial class and only one non-trivial topological class of disclination defects. Just one, you can think of it as associated with that -1 in the Z2. Now, in 2 dimensions, we have a whole set of integers describing the topology, the pi 1 topology of the liquid, 2-dimensional liquid crystal, because we're back to a circle, the structure. So now we have not just one, as in 3D, non-trivial disclination class, but a whole infinite sequence of them labeled by an integer. So it's richer. This kind of quite often happens in topology, that if you go up to high enough dimensions, you have a lot of space to move around and undo stuff. And high-dimensional topology can, in that sense, above some, depending on the problem, above some dimension, become easier. And this is kind of shown here, because you're sort of restricted when you're in 2D. You have some richness, but you're kind of restricted, and the restrictedness here gives you some topological obstructions. Now, what does the basic defect look like? For orientational order, nematic order, this is the typical pattern of the elementary defect you get. Let's start over here. You're oriented here. Now you go around, you wind 45 degrees, you go over to here, and you're out here rotated 90 degrees after going halfway around. Here, 135. Here, you're oriented. You've gone around 2 pi. This line field is rotated 180 degrees, but that's the same line field. That's the same ground state. So this defect, because you wind half of 2 pi in the literature, it's called a strength 1/2 defect, but it's the integer 1 in the class of integers, and you can have infinite number of them. Here's the winding. You go around this way, you go around that way. You wind 180 degrees going around this defect. And look at that, it has a twofold structure. It's twofold symmetry along this horizontal line. Very important in active nematics. So here's minus 1/2. Again, you have to wind 180 degrees, but in the opposite sense to any contour. And this, kind of like the vector field, has a completely different symmetry. This has a threefold symmetry, not the twofold symmetry. Okay? You have this triangular-like structure, hyperbolic-like structure, but for this RP1. That's the strength minus 1/2 defect. Now, think about it. The lowest, so in 3D, let's look at the elementary defect, which we would call, so we have 3D, we have these disclination lines, one non-trivial class, I said the -1. And let's look at the one that has strength 1, that's winding, the next one up. That would be a +1 defect. I think it's shown here. Okay, first, First, there's the structure of +1 defect in 3D for liquid crystal, has this kind of monopole-like structure. 2D, here's the winding number n equals 2, which is winding once, called +1. Now, let's look at this object here. You can have, so this object here has to be topologically trivial. We said there's only one non-trivial class, winding. So this object here, you can take and just continuously deform from that radial structure up into the third dimension and orient perfectly uniformly. That's how you this why this is not a topological defect for 3D. In 2D, if you look at the winding number object strength +1, the n equals 2 for the integer, you don't have that escape into the third dimension available to you. So there's another reason. This is how you get the whole integer class of defects for 2D, but not for 3D. No escape into the third dimension. The -1 defect for the nematic has to wind 180 degrees in the opposite sense. So you get back this kind of fourfold structure. Again, 3D can escape, 2D is stable. So the strength -1 defect is a distinct topological class. Cannot uniformly deform it into, cannot continuously deform it into the ordered state or any other defect of different strength. Since we have gone off the ground state manifold, we are talking about excited states here, excited configurations. So we are, above ground state energies in these systems, but nevertheless, you always have these configurations because of its topological robustness. So you have to deal with them. They are there, and they carry very important stuff in them through their energy and their structure. Since the energy is a gradient squared, like most system quadratic energy, that goes like the strength squared of the defect. So you have, for the case I'm describing here, 2D nematics where the elementary strength is 1/2, you have energies 1/4, then 1, then 4, and so on. Okay? This S-squared-like spectrum. And it also means that 2 1/2s have energy 1/2 live in here. So generally, half the energy of 1 + 1. So these elementary defects dominate for energetics at finite temperature, equilibrium or non-equilibrium. I said defects were inevitable. And what happens if you quench a system? When you quench a system, it's trying to order, okay? And you have domains of the ordered phase as you go below, say, some temperature for a system that can break symmetry or have a phase transition. But there's a certain size over which that order persists. If it's general relativity or cosmology, it's a light cone. Outside light cone, you cannot communicate. So things within one light cone cannot know that things outside that light cone are ordering. In statistical mechanics or condensed matter systems, there's a coherence length. There's a scale over which things can tell each other. We should be ordering, and we should be ordering on the same angle, the same inequivalent ground state. So call that, for just do a case of a circle, call that theta 1. Another domain outside the coherence length, that's theta 2. Right? It's just picking another point on the circle to order. Perfectly good ground state. Another domain has theta 3. And then they coalesce as a system tries to order globally. And you can easily compute what fraction of the time when these three domains merge will you get a defect, and what fraction of the time will you get an ordered state. So you put theta 1 here, you put theta 2 here randomly, theta 1, theta 2, theta 3, randomly on the circle. I take this as 0. And if these three angles are sort of close together, you'll see that you can continuously deform up and you come back continuously deformed to the origin. But if this one, if you have this condition, theta 3 is above pi, so it wants to reconnect this way, and the difference between theta 2 and theta 3 is less than pi, so you want to go forward rather than going back, you will, if you connect these angles with a minimum angle between them, which you want to do to minimize gradient energies, you will wind. And it's quite easy to compute in this case, since you have two regions where you're splitting in half. The probability is 1/2 for this, 1/2 for that. A quarter of the time, if you throw random points on the circle here, you'll get a defect. So that's 25% of the time. That's for a vector field. If you do that for a pneumatic, you get 1/pi. That's pretty nice. And you can do, well, we did some experiments long ago, experiments for theorists, just calling a pneumatic liquid crystal. You see these domains and you can count the length and string with 3D, and you can count the fraction of time they order, get defects, and you can estimate this probability. This mechanism in field theory and cosmology is due to Kibble, called the Kibble mechanism, but I think condensed matter theorists clearly knew it. Let's illustrate the global character of these topological defects. Look at your fingerprints. Your fingerprints are ridges. And if you look, go home, the younger you are, the better. You'll see plus 1/2 defects and minus 1/2 defects on your fingerprints. Now we're not talking about liquid crystalline order so much as just these lines, these ridges. And phenomenologically, it's known, ridges on your hand like to orient like this, sort of orthogonally to the edges of the fingers, but all the way to the tip. So let's compute the number of plus 1/2 defects, which are called loops, and minus the number of minus 1/2 defects, which are called triradians. Let's look at the excess. Since it's global, we can take any contour we want. So let's take the contour around the edges. Doesn't wind here because of the orientation of ridges, but if you go here in the space between fingers, it has to rotate 180 degrees in the negative sense. So there's a minus 1/2 defect at each spacing between fingers. So there's an excess of minus 1/2 defects by the number of fingers minus 1. And if you start from here and take your circle bigger and bigger and bigger, this number cannot change because of the topology. So it's computed by this contour here. So the number of fingers you have is the number of 1/2 minus the number of minus 1/2. The excess strength of defects is minus the number of fingers minus 1. This must be the world's most difficult way to compute how many fingers you have. And this, amazingly, this was computed by Lionel Penrose, Roger Penrose's father. In 1965, he was studying what's called dermatoglyphic topology. I don't know what was behind it, to identify something about people by these patterns, but he got this relation. And later, Roger Penrose, much later, his son, wrote a nice paper on the topology of ridge systems, which put it in sort of more modern language. But again, this shows the global characteristic of topological defects. Now, all these kinds of defects I've been talking about, which have very simple kinds of topology, the -1, the Z2 topology, just 1 and -1, the Z topology, and so on. That means that the algebra that governs the interaction of defects is abelian. They just can cross over each other. Okay? So there's no real topological intersections possible, no interesting structure for crossing. They just, integers add up, windings add up, the -1 defect just crosses over 1/2. It's like electromagnetic fields, light, that just passes over each other because you have, through each other because you have a linear-like field theory or abelian kind of structures, commuting structures in the intersection of defects. But there's another very, very interesting class of systems where you have not one, but two director fields. Okay? And it goes by the name of biaxial nematics because of the two director fields. So you have sort of one director like this, and then you have another director, like this. And then you have a third because you can take the cross product. Okay? And these two directors are different. You have to take account both of them. And you can get the structure by having a molecular building block, which is like a box, a rectangular box or brick. It's like a brick. That's one way, difficult way, because it's hard to make molecular biaxials. Or you can get the second director field by a twist axis. And this occurs in chiral nematics that have twist structures, or also called cholesterics. So there's two ways in which you can get the two director fields, depending on your interpretation. Now, this structure has really interesting topology. I've put different kinds of labeling here so that you can read the literature if you do. So I can call the three directors N, M, and then the cross product. In the literature, they're often called lambda, chi, and tau. And really, it's easiest to think of them as I, J, and K, where these are like complex numbers, and I'll explain why. So now what are the structures? You can have, say, this first director N winding, as in the +1/2 like structure, and the other one, M, and the second one, M, also winding, which means the third doesn't wind. So that's one structure. Then you can have N and L winding and not the other one winding. And the third one would be, one of the other set of pairs winding and the third one not. Or if you think of them, sometimes easy to think of a long director and a short one. So they can both rotate 180 degrees in the structures we talked about for regular nematics. Or one can rotate and not the other, and converse. The long can rotate 180 and the short not, so it's sitting up like that. Or the short can rotate 180 and the long sitting up does not. Okay? So these are the three, the brick structure has just three non-trivial symmetries, rotations by 180 degrees, and then the trivial one. Okay? So that gives you three classes plus the trivial one. That gives you these three classes. And it's actually easiest to label them by the thing that does not wind, the thing that's non-singular. So here C tau means the tau direction, or the L direction here does not wind. Here C chi means the chi direction, which is green to M, does not wind, and so on. Now, there's another one. There's one more. Remember we had escape into the third dimension by a regular uniaxial, it's called nematic. Now let's try to do escape into the third dimension, well, this is 3 dimensions, for the 3-dimensional biaxial nematic. You can do it for one director, but you cannot do it for both simultaneously because you have the other orthogonal director. So when you go up like this, you won't be able to go uniform for both directors. I should have said also for the 3D to contrast this with the 3D uniaxial nematic where we could escape into the third dimension, it also means for the 3D, the plus 1/2 defect has to be in the same class as the minus 1/2 defect, since there's only one class. Well, how does that happen? Well, you can think of the half is like a comet, right? You have this kind of structure, but you can escape into the third dimension and rotate like that and come back like that. Right? So that's how you turn 1/2 continuously into minus 1/2, and the plus 1 just going up like that is trivial. With the biaxial, you cannot do that. And you can prove that if you try to rotate both up, the structure you get on the 2-sphere is topologically non-trivial. So the radial-like defect, where you have rotations by 360 degrees here in both defects, is a 4th non-trivial class for biaxial nematics. It's usually labeled as -1, and 1 is the trivial one. So now you have 4 non-trivial classes of defects. Mathematically, if you compute the first homotopy group for biaxial nematics, you have SO3 or S2, rotations in 3 dimensions, and then you have to mod out by this brick-like structure, the 3 non-trivial symmetries of a brick rectangular box. And that's it's called dihedral group of order 2, and you can pull that up into SU2 and show that the first homotopy group is a group of quaternions. Group of quaternions that have 5 elements, well 8 elements actually, but I'll come to that, was discovered by Hamilton, 1843, where he's trying to make a 3-dimensional generalization of the complex plane. He failed because the structure is actually richer. Recently, where's my reference? I think I put it here. Anyway, recently in a paper that let me do the algebra first and then I'll come to it. Here's some pictures actually from a paper that just came out a few weeks ago with a liquid crystalline group of Ivan Smaljak at Boulder, work of his student Jason Wu, who did all the experiments and simulations, absolutely amazing, studying this biaxial system through a chiral nematic, so getting the second director from twist. And these are the pictures of the defects, these classes of defects I described. And here's a director field, here's the twist axis. So this gives you lambda, chi, tau, and then the orthogonal field. So that's what happens getting these kinds of structures, plus 1/2 or minus 1/2. They're actually in the same equivalence class, and the radial ones. That's kind of what they look like. Now, let's delve a little bit more into the algebra of these defects. If you do a 180-degree rotation about one axis and then a 180-degree rotation about the other axis, you get the third one. So I say times j gives you k, or c lambda times c tau gives you c chi, however you want to call them. So you have transmutation of defects, and the order of multiplication matters. So now the system is not abelian, but non-abelian. So you have to follow the order in which things happen. You can obviously also, if you rotate twice of 180, you come 360. So you can get the trivial configuration from 2 defects multiplied, but you can also get the radial one. Now you have the plus 1. So you get the 361, it can be uniform, or it can be the radial one. So the non-trivial one is the minus 1 element. So this means the squares of these defects, the squares of these defects give you a -1. This means now, so the algebra, if you think of it as complex numbers, I, j, and k, it's I squared, j squared, k squared, square roots of unity. They square to -1. I times j gives you k, angular momentum, cyclic algebra, j times k gives you I, and so on. And I times j is minus j times I. It's opposite. So this means two important things for these systems. One is you have networks. Now you have trivalent junctions, I times j times k. That's k times k. That's -1. So now you can have I times j times k meeting like this. You can have I squared making -1, j squared making -1, k squared making -1. All these structures in the system. You have to worry about how two defects come together, because if you go around the third defect, one goes directly to A to B defect, the other one goes around the third defect, you get a different result. Okay? So it's a very, very rich system. Networks, one consequence. Entanglement is the second consequence. Unlike the uniaxial case with the Z2, or all these integers, superfluid helium, filaments, superconducting vortices, and so on, if you try to pull J across I, like this, a braid kind of structure, you can compute with a bit of work. This was done, again, by Toulouse and Poenaru back in 1977. Clayman did a lot of work on this, lots of people, Colston, Newcastle. If you compute the obstruction to pulling these two across to blue and red like that, you'll find that there's this part here has a non-trivial topological class. And it's the class I times j times I minus 1 times j minus 1. I times j is k. This is I to the minus 1 is minus I. J to the minus 1 is minus j. This gives you k times k is minus 1. So you cannot disentangle these without producing a third defect. This means these are topologically entangled. And Toulouse and Poenaru and Toulouse called this topological rigidity. And in this paper here that just came out, we realized in the lab, and I said Jason Wu should take the bulk of the credit, all these structures for a chiral nematic, which has the same algebra, because you again have the two directors, an experimental chiral nematic system. And these are the kind of structures that you get. This is the simulation. I'll show you real pictures in a minute. So you see here, threefold junction, red, blue, and green, I, J, and K. And Jason photo patterns these so that a defect of a particular structure is patterned at the edge, the boundary of the cell, the surface. So it forms there. That dictates this one going in here. And then in the bulk, you see these junctions. Here you can have it. This is going from bottom to bottom. This is going from top to bottom, and so on. These are junctions. Junctions, that 1, 2, 3 junctions. This means that you have extended networks. It's global on global, connecting up into 3D network with trivalent vertices. And it means you cannot pull I across J, or you have to know how I has reached J, what its path is. There's path dependence. So extremely rich. Each class also has the plus or minus winding, but they're algebraically equivalent. Here's real pictures from experiments, microscopy pictures, polarizing microscopy images. Here's a chi defect and a minus one that are just crossing underneath each other. They're not being pulled across, although you can try to pull them across. It's a little tricky. This is from 3 different images, 3 different three different microscopy methods of visualizing these structures. And here you see real junctions. Here's chi times chi making the minus 1. I squared making -1, real junction there, see? And chi times chi making -1. In this case, one is a kind of a +1/2, and this one's a -1/2. Same junction here. So that's an extended network of defects. So there's this topological rigidity in the chiral nematic in the lab. And these are the kind of structures you can make now. You can have now knots and knotoids and braids, colored braids with 4 different classes and the trivial one. You have to label each element by. So this is really very difficult braiding, knotting, knotoid theory to classify these, but wonderful structures you can make. You can braid multiple times, cannot pull this across this, and so on. You can make these extended structures. Now, I haven't said anything about fantastic direction in the last, 20 years, because there have been many talks on this, but something new happens if you make the system out of equilibrium by making it a so-called active system. If you take something, these liquid crystalline systems, and now they're locally consuming energy, or they're little motors, however you want to make it. And there's orientational structure, which occurs a lot. Then new things happen, and for me, anyway, I think the most interesting one is you can create pairs of defects. Just like you can create electron-positron pair in quantum electrodynamics, you can create defects and anti-defects from nothing, from ground states, from the vacuum. And these defects are actually motile, some of them. Because of symmetries, the +1/2 defect has a non-zero, because of active flow around it, has a non-zero moment, monopole moment if you want, at the core of the defect, which gives you a vector which self-propels it. So now, pair creation, pair motility, pair annihilation, densities of defects studied a lot here and around the world. Completely new direction with, well, not new now, but a direction with lots of structure. Everyone's probably in the world has seen this defect now from Zonomir Dodgik's lab, UCSB. It's a microtubule active, a system of microtubules that bundle. The molecular motors and microtubules bundle. That forms, here you can see the nice nematic structure, and you can see also defects. And here you can see pair creation of defects from nothing. And these defects can actually move apart, even though they're attracted by Coulomb-like interactions, since they're charges or strengths. But the motile one can move apart fast enough to escape the attractive Coulomb force. And so they dissociate in a way. You get a roaming gas of vortices on top of all the turbulent active nematic flow. Many beautiful, I just don't have time to cover, but I think it's been covered by lots and lots of talks here. All the beautiful structure of active nematics, but I'll just highlight one, which I think is really cool. Here, this is showing the nematic order. Here's pair creation. See, you follow along, and here a +- pair, +1/2 pair is created, moves apart. But what creates these nematic defects? If you look at the active flow, fluid flow induced by defects acting on the nematic texture, you get fluid vortices. You get vortices here going this way and counter-rotating vortices, and they combine in directions that become highly sort of high vorticity, where two fluid vector defects meet and add up. You create the nematic pairs. So this is defects, vector field in the fluid, creating defect pairs in the nematic. defects and defects. Well, I don't think you can do much better than that, and there's a lot of beautiful work in this direction. Still being, new things are being still found and by people here. Here's just another picture from different systems. It's known in bacterial systems, all these references here. Here's for plus or minus defects swirling around. This is the microtubule kinesin system. This is a dense bacterial system. You can have vibrating rods and beads and all kinds of things. Defect gas, like the two-dimensional superfluid phase transition, Kosterlitz-Thales phase transition, the high temperature phase gas of vortices. Here's a gas of nematic defects. And here's structure, here's pairs being created and separating. So I will conclude and say topological defects are alive and well in many systems, and thank you for listening.